blanket, or this tablecloth, whatever you want to call it. Now think of this as space, or the space-time continuum. Think of this marble as Earth. When it's dropped, it distorts it a little bit, not too much. Now imagine dropping the sun. Imagine this soccer ball is the sun. Distorts it a little more. Now imagine dropping, say, a car on here. Now think of the car as a black hole. Black holes have such a great mass that they distort the space-time continuum far more than the sun and the Earth. And it is thought that at the center of every galaxy, including ours, there exists a supermassive black hole. So black holes are everywhere. Now, what this represents is the theory of general relativity, which I'll go more in depth into later. But basically, this is space-time. This is the sun. This is the Earth. And it warps space-time around it. And the greater the mass, the more that space-time is distorted. Now, what this speech will cover is how black holes form, black holes in Einstein's theory of relativity, and black holes in our galaxy. Now, basically, the way that black holes form is by the immense concentration of mass in a very small volume. Now, according to Gutierrez, a black hole is defined as a finite region of space during a period of time called space-time, subject to a singularity caused by a large concentration of mass in its interior. Now, scientists found at NASA was that the most common ways that black holes form is by a supernova explosion, and it's formed in the aftermath of a supernova explosion, so that only its core remains. And also similar is stellar implosion, which is when a dying star with its core, which is approximately three times the mass of the sun, is, since it's dying, all of the other forces, the strongest force is gravity, so it implodes on itself and forms a black hole. Now, apart from stellar implosion and supernova explosions, another way which black holes form is, well, by colliding with other objects in space to form other black holes, or larger black holes, which is also how supermassive black holes would have thought to have formed. But basically, when, say, in 2004, NASA scientists observed they observed gamma ray bursts, and then they noticed that since gamma ray bursts are large or very bright bursts of light, they figured that it had collided with a neutron star, which is also very dense, much like a black hole. And the result, supposedly, was another black hole. Now, it's interesting to see how black holes form, but to truly understand black holes, we need to understand the theory of relativity, Einstein's theory of relativity. Now, according to Gutierrez, black holes were predicted by Einstein's theory of general relativity. And there have been scientists such as Carl Schwarzschild and Stephen Hawking who have used Einstein's theory of relativity to better understand black holes. There has been more research in the 21st century, especially to understand black holes. And see, the blanket and the balls that I used earlier represent represent Einstein's theory of general relativity. Now, the greater the object's mass, the more that it distorts space-time. Now, the Stephen Hawking defined a black hole being bound within the event horizon, which is the area where it's the point of no return. And it's as wide as the radius of the event horizon is called the Schwarzschild radius, because it's the point at which the escape velocity is equal to the speed of light. In other words, nothing can escape past the event horizon. Now, another way that black holes demonstrate Einstein's theory of relativity is mostly his special theory of relativity is through frame dragging, which is when rotating objects drag space and time around it when it rotates. So, there's frame dragging that occurs when the Earth rotates, when the Sun rotates, when the Moon rotates, but it's so small relative to, say, a black hole that it's unnoticeable. And as Gary Moray described frame dragging as when rotating objects drag space-time around itself. Now, Einstein's special theory of relativity, which relates to this pretty well, is that as objects approach the speed of light, the time around it slows down. So that's kind of like twin paradox. So if someone's on Earth, but someone goes far away, they're approaching the speed of light. If they came back to Earth, they'd be younger, but their twin would be older because of the space-time distortion. Now, the black holes have been explained. Time to look at the prevalence in the galaxy. Now, NASA scientists believe that at the center of every galaxy lies a supermassive black hole, which is about 1 million to 1 billion times the size of our sun. Now, there are also stellar mass black holes, which are about 10 to 24 times the size of the sun. Now, scientists at NASA have also estimated that there are like 10 million to 1 billion black holes within the Milky Way galaxy, which is our galaxy. But there's no way of knowing for sure how many there are because they're hard to detect because you can't really see them. So it's hard. You can see their effects though. But still, there may be more, there may be less. We don't completely know. Now to conclude, black holes are fascinating features of astronomy. They are being studied by some of the most prestigious physicists of the 21st century. And it's amazing how so much mass can be concentrated into such a small volume so that its center or its singularity are infinitely dense. Now, Einstein had inadvertently predicted black holes when he developed his theory of general relativity. And now scientists have used that to better understand the universe, to better understand how everything works. But it is absolutely essential to understand black holes. Now, scientists still don't completely understand black holes, but that only means that there's exciting room for research.